Analysis of protein are either via electrophoresis or paper chromatography, and those are how you can detect primary structure of proteins. There are two steps that are in common in both. The first step is what you need to do before you either do electrophoresis or paper chromatography, and that's protein hydrolysis by 6 molar hydrochloric acid and heat. Now, hydrolysis, you're going to break them into their separate amino acids. Next, you're going to place the sample of your amino acids in a gel, in polyacrylamide gel, in a buffer solution. And I'm going to show you one example of separation of 5 amino acids. Now, the amino acids will migrate toward the different electrodes depending on their charge, and the molecules migrate at a speed due to their attraction to the gel and then their affinity for the voltage. In paper chromatography, the sample is placed at the bottom, almost the bottom, 1 centimeter away from the edge of the paper. Separate spots of known amino acids are placed alongside because you want to know if your mixture contains those. And I'm going to show you this process to make it easier to comprehend. The paper then is placed in a solvent known as mobile phase. Your paper is known as stationary phase. The spots of different amino acids partition themselves between the two phases at different rates. Those are which are soluble in your mobile solvent, they travel further. Those that are not so soluble and they have low boiling point, they usually have affinity to be absorbed by the paper. Now, when solvent nears the top, the paper is removed and dried. The last step, which is common then again for both processes, is you need to develop this. You need to make them shown by spraying a solution known as 9-hydrine. So we use this solution in order to stain them so we can analyze them. Now let's look at one example of electrophoresis. For example, here we have 5 amino acids that we like to separate from each other. We know the mixture has this. First, we are going to pick and choose a buffer. The buffer was chosen to be same as one of the amino acids here. Now, if you look at this amino acids, it's going to stay in the center and not move. So this will be SER. Why is that? Because this is the place that it's a Zwitter ion. You have a positive and negative charge accordingly, and it's not going to move in any direction. Now, if you look at those that are 7.6 and 10.8, which are bigger than your buffer, this is the case that the buffer is going to behave as an acid and donate its H to COO-. So in this H here, you are going to have a positive charge which is going to be attracted to the negative electrode because your buffer is acting like an acid by donating a H. Therefore, there is only a positive charge. Now this here is your ARG because 10.8 is much bigger than 7.6, and 7.6 probably stops somewhere of this neighborhood. So this is how they are going to separate relative to each other. Now if you look at the other two extremes, you see our buffer is basic compared to their isoelectric point of these amino acids. So what happens in this case, the buffer behaves like a base, and you are going to take the H from the amino acid. So this side you're negatively charged. Therefore, it makes sense that you're going to be pulled by the positive electrode. And what happens? This is 3.2. This will be GLU, and this is 5.5, which is PHE. So they will be separated like this. You will spray it with 9-hydrine, and then you're going to study it according to the standards you have. Now, looking at paper chromatography, briefly to talk about it. So the sample is placed somewhere here, and then you put your known amino acids, and you put it in a container that has solvent. You will cover it up so there is no evaporation. The solvate is going, due to capillary reaction, going to travel on this paper, go up, and then here, this is where you stop. And when you take it out, you let it dry, then you spray it with 9-hydrin, and then the spots are going to show, and you're going to calculate retention factor. In biology, I don't know why you call it retardation factor, and it's distance traveled by the sample. So for example, if you look at the blue dot, this is the distance traveled by the sample divided by the distance traveled by the solvent. It's always less than 1. And when two spots have the same identical RF, you can assume you have that amino acid in your mixture.